Hello, ladies and gentlemen. Today we are going to be taking a look at solving absolute value equations and inequalities. For this, you're going to need to take really good notes today, okay? There's a lot to write down, and if you're not listening with your audio, you're going to be very confused. Now, I know that many of you who are listening with your audio and heard me say that will be okay, but I've noticed that little prompt on the bottom to kind of remind people to make sure that their audio's on. We need to be listening as well as watching, okay? So let's first talk about what you already know about absolute value. So you don't need to write this part down, but you've already been told or are aware in your math career that absolute value represents a distance from zero. So the absolute value of a number, any number, including this number 3 right here, if I were to take the absolute value of 3, what I'm asking myself is how far away from 0 is the number 3? And that would just be 3, because 3 is 3 units away from 0. But on the other side, you could have the absolute value of negative 3. Well, negative 3 is also 3 units away from 0, so his absolute value is also 3. When we're talking about absolute value, we're really talking about a distance away from 0. And that's why you would always hear people say an absolute value can't be negative, because of that idea that you're talking about a distance. So how do we take what you already know here then and apply it to how we solve an equation that contains an absolute value? Like this one, we have the absolute value of x plus 2 is equal to 5. So first thing I'd like you to get in your notes is this idea of solving the equation can be done using a graph. If you so choose, you could do this. So in your notes, if you would, let's write down this first example here. We have the absolute value of x plus 2 equals 5. And so what we would do here, guys, is we would take a look at just this absolute value part and use what we already know about how to graph. So if I were to take just that part and think about him as just an absolute value function like you see there, remember our shifting. This really means he shifts over to the left 2, and we'd have a nice little slope of 1 over 1 there. Nothing being added to it, nothing too fancy, so we're just going to draw him in here. And if I just draw in this absolute value, v, and I connect these dots here, what we're talking about is this absolute value function. And what we want it to do is we want to know where does this absolute value function have y values that are equal to 5. So where would it be equal to the y equals 5 line? So I'm kind of dashing that in here. So if we were to try to answer that question, remember back a while we talked about when two functions are equal, we're talking about this intersection point right here and right here. But we don't want to know that that's 3, 5. We want to know what is the x value that corresponds with this point and this point. So I can see that I have two x values, one at 3 and one at negative 7. There are actually two solutions to every absolute value equation that we're going to run into, or two ways we're going to get that solution, I guess I should say. And we need to be aware that that stems from this idea that this is the way the absolute value looks. It's got two sides, okay? And so we're going to use that idea to help us find those two solutions. Will we need to do the solutions with drawing a graph every single time? Is there a way to get the solutions without the graph? Yes, there is. And we're going to take a look at that now in this video. All right, so here's your second example we need to get into your notes where we're not going to draw a graph. Instead, we're going to do a couple steps that you're always going to do anytime you're trying to solve something that has an absolute value. The first thing is to isolate the absolute value. So first thing, you need to isolate that absolute value. That means get the absolute value alone. And then the second thing we need to do is set up two problems. One for the negative sloping side of that absolute value function if we were to graph them, and one for the positive sloping side of that absolute value graph if we were to graph him. So negative slope, positive slope. And so we're going to think about that today when we're setting these two up. So first, let's start with isolating this absolute value. So if I were going to go ahead and isolate this absolute value here, that means I would leave this part alone and try to eliminate this plus 5. And I would do that by subtracting 5 first, and I'd end up with the absolute value of 5x minus 10 equals 45. Okay, so I've isolated the absolute value. Now once I've done that, I need to set up two problems. So I'm going to take what I have written here. The absolute value means something, guys. It's not just like parentheses. It means we're going to go ahead and do this whole keep one side positive, do one side negative business, okay, when we set up these two problems. So the first thing I'm going to write is for the positive part. I'm going to keep the 5x minus 10 as they are and set it equal to 45. The other problem I'm going to set up still has 5x minus 10 equals 45, but we're going to negative one part of that, or that whole side, because that is the absolute value part. The 5x minus 10 is the expression that was in the absolute value. So that whole part, that whole side over there gets a negative, okay? So let's go ahead and solve this first side. I'm going to add 10. I'd have 5x equals 55. So x would equal 11. There's one solution. And now the other side, I'm going to distribute this negative sign. So I'd have negative 5x plus 10 equals 45, minus the 10 away then. So I'd have negative 5x equals 35. If I divide by negative 5, x equals negative 7. Now, a lot of times people will say, well, wait a minute, I thought absolute value couldn't be negative. Well, this is not absolute value. This is what x equals. So if we were going to plug it into the original equation, I would end up having absolute value 5 times the x was negative 7 minus 10, close the absolute value, plus the 5 equals 50. That was the original equation, which is this negative 7 plugged in. Well, negative 5 times negative 7 is negative 35. Minus 10 more is negative 45. So I'd have the absolute value of negative 45, that's 45 plus 5, does equal 50. See, it works. Because we're not talking about absolute values being negative, we're talking about the x to be a negative value, and that's okay. So now let's look at this third example here on solving equations. This one has an interesting part to its directions that we need to talk about. This part right here, extraneous solutions, means you have extra solutions that don't actually work. So you need to check those solutions to be sure that they actually work in the context of our problem. So we're still going to go ahead and do this the same way. This problem already has the absolute value on this side isolated, so we'll just go ahead and write the two problems we're going to use. So 2x plus 12 equals 4x, and also a 2x plus 12 in parentheses with a negative equals 4x. So if we solve both sides here, or solve both halves, we're going to subtract 2x. So I'd have 12 equals 4 minus 2x is 2x. Divide by 2, x is 6. So x equals 6. And the other side, I could go ahead and distribute the negative sign. Minus 12 equals 4x plus, or actually I think I'm going to add the 2x here. Negative 12 equals 6x. Divide by 6, and x equals negative 2. So I have two solutions again, but there was this big clue in my directions here that says, you know what, we have an extraneous solution possibility, which means we could solve this completely correctly, but one solution might not work in the context of the way this problem was written. So if I go up to the very top here and keep this problem in mind, I'm going to rewrite that with the 6 plugged in, because it could be the 6 that doesn't work. So if I plug the 6 in, let's go ahead and calculate here. 2 times 6 is 12, plus 12 more makes 24. This side is the absolute value of 24. What is the absolute value of 24? 24. Now if I go to the other side, 4 times 6 is 24. If I drop that value down, do I get something that makes sense? 24 equals 24? Yes, it checks. Now let's do the same thing with the negative 2. 2 times negative 2 plus 12, absolute value, minus 4 times negative 2. This side first, left side first. 2 times negative 2 is negative 4, plus 12 more would be 8. This side gives the absolute value of 8. The absolute value of 8 is 8. Now let's go to the other side. 4 times negative 2 is negative 8. If I drop it down, is 8 equal to negative 8? No. So that means this solution, while we solved it correctly, is actually extraneous. It doesn't actually work in the context of our problem. We would want to cross it off and not let people believe that that's an actual solution. So now that we have a handle on absolute value equations, remember there's two sides, two problems to solve. What if that equal sign turns to a greater than or a less than sign? Does that change my approach to solving? Well, let's take a look at some inequalities. Don't write these down, but I want you to see how this works out graphically. Again, I could take this absolute value piece right here and go ahead and graph him shifted over, because this would actually shift over to the left too. Do-do-do, do-do-do. So now if I have this V right here, and it says I want to know on that absolute value graph what x values are less than or equal to 4 right here on that absolute value function. So here's the line that represents 4, where y is less than 4. So what x values would be less than that line? Well, all of these, you guys, right? I mean, it's not just equal to that spot, but it's less than this whole area down here. So from like -2 to 6, there's this whole region of x values that make that happen. And the same thing goes for when we have not even less thans, but greater thans. If I were to graph this one, same idea. I'm going to shift over to the left one here. Over to the left one here. Nice easy slope, so that's good. Here we go. This says I want to know where is it greater than or equal to 3. If here's my 3 line, look at this. Greater than that 3, greater than that 3. Again, there's a region of x values that make that happen. And this region happens to be two separate parts, not together like that other region, not in between two numbers, but where x is greater than or equal to 2 and where x is less than or equal to -4. So how do we go about getting these regions of x values, if you will? Same idea as we were doing before. That's the good news. So let's go ahead and write this fourth example down back into your notes now. And this time, instead of having an equal sign, notice we have a less than sign. But the good news is it doesn't change our strategy. Is the absolute value isolated? Yes. Then we would write up our inequalities, our first inequality and our second inequality. The first one is where that 4x plus 5 remains unchanged. And it's less than or equal to, oh, sorry, this should be a 13 right here. 13. Okay, and then the other side is, what do we do with that 4x plus 5? Well, we just make it negative, right? And that's less than 13. So now if we solve each one separately, we're going to go ahead and do that. We'd have 4x, 13 minus 5 is 8, x less than or equal to 2. And the other side, if you would like to distribute that negative sign, you could divide it off as well. I'll show you that on the next example. We'll have 4x minus 5 less than 13. We'd add the 5 over. We'd have -4x less than 18. Divide by -4 now. Now be careful when you divide by the negative on those inequalities. That flips that sign around. 18 divided by 4 is 4.5, so this would be -4.5. So we have two parts to our solution here. So let's take a look at their sketch on a number line, see if we can make sense of this. We need to have 2 on our number line. We also need to have -4.5 on the number line. I'll probably maybe throw a 0 in here for perspective a little bit. And we're going to have an open dot at 2. And this one says x is less than or equal to 2. So we're going to go ahead and draw where all of that would be here, going this way. And this one says where x is greater than or greater than -4.5. Greater than -4.5. So look what happens here. We're talking about this and situation where it's in between those two numbers. That's like that first graph we were drawing. So where all of our solutions are in between -4.5 and 2. So how would we write that as an interval using the parentheses and the brackets we were talking about? Well, you would just say from -4.5, comma, 2. And we use parentheses there because it's not including the values of 2 and -4.5 because it's not equal to those with our inequality. All right, so let's take a look at a fifth example, last one. We're going to solve this inequality. This one has a greater than sign. So x plus 4 in the absolute value is greater than or equal to 6. Is the absolute value isolated? Yes. So we can go ahead and set up our two inequalities here. So we would say x plus 4 greater than or equal to 6, and also x plus 4 with a negative greater than or equal to 6. So if we solve them separately, I'll go ahead and subtract 4, x greater than or equal to 2. I told you I'd show you how you don't have to distribute. This is negative 1 times this. If you want to divide by negative 1 right away, that would cancel that part out, and you'd have x plus 4. Be careful when you divide by a negative, though. You still have to flip that sign around, and this side becomes negative 6. So we'd subtract negative 4 here, or we subtract 4. You'd have x less than or equal to negative 10. So if we were going to sketch the solutions right here, we'd have negative 10 on my number line. I'd also need to make room for 2. Maybe 0 would be way over here now this time. And now we need to, again, put those dots on there and sketch what this looks like. We'd have a closed dot at 2. And I'd need to show where x is greater than or equal to 2. So that means it's going this way. And at negative 10, I'd have a closed dot as well. And I'd be going x less than or equal to negative 10, so that'd be this way. This is one of those OR situations. My solutions either come from this side or this part over here. So be careful when you're doing these. Sometimes they're in between the two numbers, sometimes they're ORs. We'll see in class if you can figure out which time it's going to be the OR and which it's going to be the AND, okay? So let's write as an interval here. This one's a little bit trickier because we have two locations here that are separated. So this part right here, the interval there would be negative infinity, right? Because that's negative infinity it's pointing at, until negative 10, and the bracket at negative 10 because we're including negative 10. The other side, 2 until positive infinity forever. Okay? Nice. And you can write the word or in between here. There's also some special notation you'll see later in other math classes that we can show you in class as well. Okay, so this is the basic idea for solving inequalities and equations. Remember, two problems really for each problem that you'll be doing. Okay, two halves or two parts to solve. All right, I want to thank you for taking good notes today.